Okay, here goes another one. Section 2.4, multiplication of matrices. This section's a little bit more challenging than the previous one, and I will skip some of the notes because I go into too much detail and I don't really think it helps. So I'll let you know when we're skipping things. So just a few more concepts about matrices that you should be aware of. The transpose of a matrix is created by turning each row of the matrix into a column and vice versa. So the transpose of matrix A is written as A with a superscript of a T for transpose. And again, a transpose is formed by turning each row into a column. So row 1 becomes column 1, row 2 becomes column 2, etc. So if A is the matrix 1, 4, negative 8, 0, 9, 5, then the transpose becomes row 1 becomes column 1. Yeah, that's true. And row 2 becomes column 2, row 3 becomes column 3. So the 1 and the 4 gets put long ways into a column. The negative 8, 0 is long ways into the second column. And 9, 5 goes down and becomes the third column. Another important thing that we'll talk about is an identity matrix. An identity matrix is a square matrix. So again, a square matrix is when it has the same number of rows as columns. And an identity matrix has 1s on the main diagonal and 0s everywhere else. In general, I sub n implies the n by n identity matrix. On the next page, I'll show you some examples. So I1 means the 1 by 1 identity matrix, and it contains just the single scalar value 1. I2 is a 2 by 2 identity matrix, with 1s along the diagonal and 0s on the other diagonal. I3 is 1s along the main diagonal, but it's a 3 by 3 matrix, and 0s everywhere else. Scalar multiplication is pretty straightforward. Scalar multiplication of a matrix simply means multiplying each element of a matrix by the same number. A scalar is really just a constant. We discussed the negative of matrix A, or its additive inverse, we called it, by taking the opposite of A, and that really just meant that you multiplied each element in matrix A by the number negative 1. So to take that idea and expand upon it, if matrix A is 1, 6, 7, negative 5, negative 3, 8, negative 2, 10, 3, negative 2 times matrix A just means that you will multiply each entry in matrix A by negative 2. So the positive 1 that you have in the first row, first column, times negative 2 is negative 2. 6 times negative 2 is negative 12. 7 times negative 2 is negative 14. Negative 5 times negative 2 is this positive 10. Negative 3 times negative 2 is positive 6. 8 times negative 2 is negative 16. Negative 2 times negative 2 is positive 4. Negative 2 times 10 is negative 20. Negative 2 times 3 is negative 6. So in general, the product of a scalar, a number, times a matrix, k times A, is the matrix A with each element in that matrix multiplied by the constant k. So if I give you matrix C that contains the elements 1, 7, 4, negative 5, 3, negative 9, 1, 4, negative 11, to find 3C, you would simply multiply matrix C by the number 3. Oops, I should write that first. So 3C would equal, and it doesn't matter if you use square or round braces for your matrix, it's your preference. I really prefer the square ones. You take each first row element by 3. So 1 times 3 is 3. 7 times 3 is 21. 4 times 3 is 12. 3 times negative 5 is negative 15. 3 times 3 is 9. Negative 9 times 3 is negative 27. 1 times 3 is 3. 4 times 3 is 12. Negative 11 times 3 is negative 33. So far, not so bad. When we get to multiplying two matrices together, that's where things get a little bit more complicated. And I have this complex example of two different bookstores selling two different kinds of books. And I've tried it before, and I really don't think it's all that constructive in telling you how to actually do this. It gives some rationale as to why you multiply matrices the way you do, but I think it's really just more confusing than constructive. So we're going to skip page 3, and I think part of page 4, if not all of page 4. So yes, we'll skip most of page 4 until about here. Okay, so we actually also need this sentence right here, this paragraph. If there are several rows on the left and several columns on the right, then we multiply each row by each column with each answer placed in the product matrix at the row and column position from which it came. It's not going to make much sense until you see it done. So I'm really just going to skip ahead to an example, and you'll see what I mean. I did miss something, though. I have to tell you about the size of the matrices. And the thing I need to tell you is right here in this note. Unlike adding matrices from the previous section, which I hope you remember, they had to be the same exact size for you to be able to add two matrices together, the same size, the same shape. When you multiply matrices, they have to have compatible sizes, by which I mean, if your first matrix is an m by n, the second matrix has to be an n by something else. Whatever number is here, whatever the number of columns from the first matrix is, must match the number of rows of the second matrix. So now that we know what is meant by compatible sizes, we can go about our business in trying to actually multiply two matrices together. It's not as direct and easy as you might think it is, but we'll go very slowly. So what is the size of this first matrix? It seems to me like it has a single row and then 1, 2, 3, 4 columns. So this is a 1 by 4 matrix. I don't know why I cannot do these X's. The second matrix has 1, 2, 3, 4 rows and only a single column. What you were looking for is if this number matches this number. It does. What ends up happening, oops, I didn't tell you what ends up happening, is that these cancel out and you end up with a 1 by 1 matrix. So those two numbers have to match and you end up with whatever number is here, oops, by whatever number is here size matrix. So we know we're going to end up with a 1 by 1 matrix. It means there's going to be a single entry. But how do we get that single number from all these numbers being multiplied together? So I like to think of it as some sort of odd type of distribution. I start with the number 1 that's here. So the first entry in my first matrix will get multiplied by the first entry in my second matrix. So I take 1 times 3. This is where matrix multiplication starts to get weird. Then you add. You then go to the second entry in your first matrix and multiply it by the second entry in your second matrix. 1 times 2. Plus. The third number gets multiplied by the third number. I'm out of space again. I need to erase this line. Plus the last number, which is this -1, gets multiplied by the last number in the second matrix. So it's plus -1 times +1, I think. Yes. And then you simplify this. 1 times 3 is 3. Plus 1 times 2 is 2. Plus -1 times 4 is -4. Plus, I think I lost the negative. This should be -1 times 1, which is -1. You end up with 3 plus 2, which is 5. 5 minus 4, which is 1. 1 plus -1 is 0. So then moving on to our second example, which is obviously a little bit more complicated, you have to first check that the sizes are agreeable. The size of this first matrix, this has 1, 2 rows, and 1, 2, 3 columns. So this is a 2-row by 3-column matrix. This next matrix has 1, 2, 3 rows and 1, 2 columns. So this is a 3 by 2 matrix. You are supposed to check that these two numbers are the same. They are. They will cancel out, and you will end up with a 2 by 2 matrix in the end. So corresponding to that, what I like to do is I like to start by creating a matrix that has 2 rows and 2 columns. So I kind of know where I'm putting my answers. Now, let's also pay attention to what's happening. This is row 1, this is row 2, this is column 1, this is column 2. Row 1, column 1 comes from multiplying row 1 with column 1. Row 1, column 2 comes from the previous 2 matrices multiplying row 1 with column 2. This will be row 2 with column 1 and row 2 with column 2. So back to where we were. What I mean by that is this is row 1 right here. Row 1 will get multiplied by column 1 in that same strange way. This 1 will get multiplied by this 2, the first with the first. And since that is row 1, this is just really tiny. This is row 1. And this is column 1. Row 1, column 1 comes from that row being fed through that column. So you have a 1 times a 2. Oops, I didn't mean to do that. It's a 1 times a 2 plus this 2 times this 3. So you're going across and down. 2 times 3 plus 1 times 2. Now you are done with row 1 and column 1. I'm going to erase what we just circled so it will be less confusing when we start over. But just check out the corresponding color coding before I do anything. Alright, so now I'm going to erase those so we can start over. Now we are looking and coping with row 1 and column 2. So that's row 1 still, and that will get fed through column 2. So the first thing in row 1 goes to the first thing in column 2. The second thing in row 1 goes to the second thing in column 2. The third thing in row 1 gets multiplied by the third thing in column 2. And it goes in the block labeled row 1, column 2. So the 1 gets multiplied by this 2. 1 times 2 plus